Now we're going to talk about redundancy. We're going to talk about the safety notation, classic architectures, new advanced architectures, and then we're going to do some comparisons between them. Redundancy was absolutely an essential design requirement, even in the earliest microcontroller designs. First one I heard of was a Honeywell TDC 2000 in 1976. Two redundant sets of equipment to accomplish the same job. Boy, that sounds like a lot of money. I mean, why would you spend 2 or more times the money when you don't need to? And the answer is you want one to keep running when another one fails, because keeping running is worth the money. That's what the redundancy was for in these early distributed control system designs. But what's the real advantage of the redundant architecture? And are there any disadvantages besides spending more money? I say let the numbers answer the question, and we're going to do some of that in this session. I'd like to explain the notation commonly used in safety instrumented systems. KOOM. K is the number of M is the number of equipment sets, and K is the number of sets needed to perform the safety function. And now's a real good time to explain the difference between safety and availability. That DCS controller we just talked about, that's for availability. That's to keep things running. That's not for safety. In safety, in a de-energized to trip system, and don't forget, as you're getting yourself all wrapped up and confused in this, remember de-energized to trip. We'll talk about that more. I have 2 sets of equipment. I only need one of the 2, 1 out of 2, to perform the safety function. Okay, we are ready to roll. I'll start by explaining a classic 1001 non-redundant system. This is a safety system. Let's assume we're talking a sensor, a controller, and for the moment, the output of the controller. Let's focus on that output. If this controller runs properly and there's a demand, the switch will open circuit, de-energizing the final element. Make sense? If there is no dangerous condition, the sensor says everything's okay, switch closes, and the final element is energized. Energized, okay, de-energized, trip. Now, if we pick some standard, just some numbers, some round number failure rates, and use a test interval of 1 year, and we use some simple numbers and some simple equations, we would calculate a spurious trip rate of 0.01 per year and a Ph.D. average of 0.01 for a test interval of 1 year. Now, I have to stop and warn you, we are using simple approximation equations. There's no common cause, there's no diagnostics, there's no proof test coverage, and all of the other key variables for a Ph.D. calculation. So you ask, why use these simple equations? They are the best to use when explaining the differences between architectures because we can keep the math simple. Just don't use them for real Ph.D. calculations. Now, what if you were designing a system and this 0.01 Ph.D. is not good enough? Well, first thought that pops into many engineers' head is, aha, I will wire 2 controllers in series. Why do I wire them in series? If one fails, dangerous, The switch is jammed, closed, and will not open. The circuitry driving the switch may not allow the switch to open, but the bottom line is if there's a dangerous condition and one of these systems has failed dangerously, the system in a 1 out of 1 will fail dangerously, but here I have another one, and it's wired in series so it can de-energize the output. Make sense? Only one of the switches has to de-energize the output. That's why we call it 1 out of 2. What's the equation? I mean, is this really any better or not? Using the same simple numbers, the spurious trip formula is 2 lambda s, and we get a 0.02 per year. False trips are not good. O2, I don't like that. But let's check Ph.D. Whoa, 0.00013. That is amazing, isn't it? Simple equations, no common cause, no diagnostics yet. We're just comparing. So it looks like this is a wonderful solution to the safety problem. But I don't like that O2. Yeah, in fact, the DCS redundancy was more like 2.002. I wire 2 switches in parallel because I don't want the failure of a switch open circuit to de-energize the output. I got to keep this final element energized to keep the plant running. Solution to that problem, 2 out of 2. If one switch goes open, the other switch still energizes the output. Problem solved. Great. Uh-oh. And it is, look, 0.0001 per year. This is fantastic. My Ph.D. average just doubled from 0.1 to 0.2. Now, how do we solve this problem? This was a real problem solved by engineers decades ago. The solution that originated in the 1930s was 2 out of 3. 3 sets of equipment. 3 sets of equipment, are you insane? Some manufacturers called this TMR, triple modular redundancy. Their competitors called it TMR, too much redundancy, because it was expensive. I've got 3 sets of electronics here. Is it worth it? Look at that output switch. This works because not only is there 3 full sets of electronics, but each set has 2 output switches. We take those 6 switches and wire them 2 in series and 3 sets in parallel. Think about it a minute. Think about it a minute. What if the A subsystem fails dangerously? Okay, short out those 2 A switches. Can the set of 6 switches still de-energize the output? Yes, because B and C are still working, and if A is shorted, we still can de-energize, even though one has failed safely. What if one fails safe? Okay, let's stick with A. The A switch is open circuit. Does the final element remain energized? Yes. Why? Because B and C continue to supply power to the final element. So I can tolerate a safe failure or a dangerous failure. Kind of a nice design, really. Think about it. This is the same concept, the exact same design implemented in the space shuttle, which was designed during the late 60s, early 70s. Using simplified equations, let's calculate spurious trip rate. 0.003 That looks pretty good, but you know what? It's not nearly as good as 2 out of 2. Look at that difference, 3x. That's a trade-off. Why do you get 3x? Well, I got 3 sets of switches wired in parallel over here. And of course, now I have 3 times the total failure rate and 3 times the maintenance expense, but look at the advantage. What about Ph.D. average? 0004, that's pretty good, but it's about 3 times worse than 1 out of 2. Does that make sense? Actually, yes. Why? Because I have 3 sets of switches wired in parallel. It all makes sense. This is, however, an architecture at least looks pretty good when you compare safe and dangerous failures. I have a question for you. What if I get 2 safe failures? What'll happen? System trips. Cannot tolerate more than 1. Don't think of this architecture as something as, well, I have 3 of them, so 2 of them can fail and the system still works. No, no, no. What happens if it's a dangerous failure? If 2 of them fail danger, like A and C, that element gets energized all the time, no matter what. So it only tolerates 1 failure in each of the failure modes, safe and dangerous. It was really the only way to go if you needed safety and availability in the early 70s. And microcomputer engineers started thinking how to take further advantage of the fact that we have a computer and I can program it and I can figure out when it works and when it doesn't. Automatic diagnostics. Boy, the earliest automatic diagnostic papers I've seen come from the late 60s, early 70s. So this whole movement was occurring at the same time at the same time when there was only a 2 out of 3 solution available. It enables online repair, automatic detection of the failure, tell the repair people, come and fix it. It enables automatic shutdown. If you need to shut down on a dangerous failure, program the automatic diagnostics to do exactly that. And we can build new architectures by using the automatic diagnostics. All right, how good are they? Are they really worth bothering with? Why in the world, if I've already got a 2 out of 3, would I want some new architecture? First architecture is 1 out of 1D, and the D means there is a diagnostic switch. The D was not added to indicate diagnostics, because virtually every microcomputer has some diagnostics, maybe a little or maybe a lot. The D means, what do you do with it? You de-energize an output. That's what you do with it. Look at this. A diagnostic switch is wired in series with the main switch. If you've got it programmed to automatically trip on a detected failure, the diagnostics will say, it doesn't work anymore. Open up the D switch, output de-energized, fail-safe. That's what I mean by converting dangerous failures into safe failures. Now that was interesting. In fact, in the early days of using PLCs for safety, many engineers thought of the idea of putting in a watchdog timer. Maybe you still see some designs today that use this external watchdog timer. That was a D. The logic solver would send a pulse up to this timer. As long as the pulse kept coming in the expected time period, the switch stayed closed. If the pulse went away, de-energize the output. concept, the pulse goes away if the processor fails. And it was very strictly enforced in many safety system designs during the 70s and early 80s. We're going to take a look at these designs. A natural evolution of that is to simply take two of these 1 out of 1Ds and wire them in parallel. So even if there's a diagnostic failure on one, the other one can keep the plant running. 2 out of 2, remember? And this is the classic architecture actually used by most of the early DCS controllers. 1 out of 2D realized that, gee, there's a little bit of an issue here. If I get a dangerous failure in both sides, system fails dangerously. Unless the diagnostics in one machine can control the diagnostic switch in the other. So extra control lines were added so that each machine can not only control its diagnostics, but his friend's diagnostics as well. That substantially improved the safety over the 2 out of 2D. If we take a look at this 1 out of 1D, and remember, we're not sure about these architectures yet. Are they any good or not? 1 out of 1D, using simple formula, if we get a failure, we will de-energize the diagnostic switch, and we would expect this number to be higher than 0.5, and it is, 0.62. And we would expect, boy, not much difference between 1 out of 1 and 1 out of 1D on the Ph.D. average. If the coverage factor is more like 60%, 60% of the failures are detected. And that's exactly the kind of a coverage factor you would get from a watchdog timer. Just having a pulse doesn't detect, 60% of the failures in a computer, that's not bad. That's a majority. But the numbers tell us it's not so effective. Well, what if I had more like a 95%? Now we're talking. It still only goes from 0006 to 0005, and the spurious trip rate goes up even more. Yeah, that would happen. I don't know about you, but I would conclude the concept of a watchdog timer is really of little to zero value. Seems to me all it does is increase the spurious trip rate for no improvement in safety. Well, I still like the idea of diagnostics, and maybe if we use more realistic equations, it would look better, but so far, this diagnostic thing doesn't look so good. What about this 2 out of 2D? Remember, what we were worried about there was the increase in the spurious trip rate. Well, if we look at these simplified equations, 1 out of 1 had an 0.5 with these particular variables. 2 out of 3 had a 0.0043. Nice. 0.006 and a huge number of zeros. This is really safe. 1 out of 1D had the 0.69. My 0005. 2 out of 2. Oh, this is not bad. 0.0021. It's better than the 2 out of 3. At, what's the coverage factor here? 95. Ph.D. is 0.001. That's not that good. Of course, that's exactly what you'd expect. You put two of these in parallel, you should get a 0.001. All right, I'm not sure about that architecture, but it really worked well for a DCS controller. I'm not so sure if it's a good idea for a safety system. And of course, that was exactly what designers concluded. And they added the extra control lines for a 1 out of 2D. And let's look at this simplified equation result. 2 out of 3, 0.0043. 1 out of 2D, I still got the 0.0021. That's good. That's better. Geez, the Ph.D. looks great also. We got to count these. 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. At 95% coverage, this is better on safety also. And that's what designers concluded in the late 80s, where this kind of an architecture became commercial. Today, in the 2010s, and as we head for the 2020s, architectures have become far more advanced. They're hybrids. These old notations just fall apart. There was some attempt to create notations like 2 out of 1 out of 2, but this really doesn't communicate very much. New architectures are combinations of 2 out of 3 and 1 out of 2, and the electronics are becoming so effective, and the diagnostics are becoming highly effective, such that you're never sure what it is, so it really needs a good, thorough technical evaluation on some of these newer architectures. Well, what's best for safety? 1 out of 1, 1 out of 2D, or 1 out of 1, 1 out of 1D, and 1 out of 2 have very high spurious trip rates. That's fine for things like machine safety, where a spurious trip is not a big deal. Your robot stops moving, you reset, get the person out of the light curtain, and it starts running again. So 1 out of 2 is probably a good safe architecture, and if you don't care about spurious trip rate, this is a common solution in the machine safety world. In process industry, we must have a low spurious trip rate because shutdown of a process unit might not only create dangerous conditions, but it might be very costly, far more than extra controller hardware, actually. Now, the 2 out of 2D could be effective if it has very good diagnostics, even greater than 95%. To get a 2 out of 2D to be effective, you really need to be in the 98 or 99% range, and that's kind of hard, even today. But we're getting there. 1 out of 2D is probably the safest architecture of all, but the spurious trip rate is slightly higher than a classic 2 out of 3. In the late 2010s, we see commercial implementations of 2 out of 3 still on the market. We see commercial implementations of 1 out of 2D still on the market. And 2 out of 2D is becoming more of a common design as the diagnostics really do approach 99 and even higher, because semiconductor companies are now helping. Redundant architectures are worth the money. However, remember that we did not use the 8 variables needed to calculate a realistic Ph.D. average for process industries. If we do that, we may have slightly different results. And of course, it depends very much on your particular application. If you have any questions, send an email to exida. Thank you.